So hello everyone, I'm going to speak about the new native histograms in Prometheus. I'm Ganesh Vernekar, I'm a Prometheus team member and I work as a software engineer at Grafana Labs. Before starting to see what are native histograms, let's see what are histograms first. Histograms is a distribution of all your observations in specified time ranges. We call them buckets. In this particular example, the first column tells you there are 15 requests that took less than 0.1 seconds. Similarly, this blue column tells you like 25 requests were between 0.1 to 1 seconds. And last bucket is a special one which encloses everything that was more than 2 seconds. And this is how we store it in Prometheus right now. We have a separate time series for each individual bucket, and the last and we use something called the LE label, which means less than or equal to, and all the time series are cumulative. For example, if you look at the time series which says LE equals to 1, it says 40 and not 25, which means it's everything that's less than 1. So if you want the count between 0.1 to 1, you have to subtract 40 with the previous time series. And we have two more time series for this, which is the overall count and the overall sum of observations. So this is how it is done in Prometheus right now. But this is how native histograms will be stored. It's a single data structure with everything that has to do with histograms. We will take an example. I will show an example of how the native histogram looks like. But to go over these very briefly, the histogram has count and sum like before. It has a schema which defines what the bucket boundaries will be. The 0.1 seconds and 1 second, all those things we call as bucket boundaries. And yeah, schema defines what the bucket boundaries can be. The positive spans and negative spans are just something which tells you which buckets are filled. And positive spans are for positive observations, negative spans are for negative observations. And positive buckets and negative buckets hold the actual observations in them. We'll ignore the other two parameters for this talk, but now let's see how do we store these native histograms. Let's start with schema because that's where everything starts. So with schema, we get something called a ratio, whose formula is 2 power of minus schema. We'll see why this 2 power of 2 power is required later. And this ratio defines what's the ratio between a bucket boundary and the bucket boundary of a previous bucket. For example, if the bucket boundary of the current bucket, like the upper bound was 1, then the upper bound of previous bucket would be the 1 divided by the ratio. And schema goes from 8 to minus 4. And the lower the ratio, higher the resolution of the histogram, like the jump between two bucket boundaries is very small. We'll take an example. We'll see how this schema actually works. Like if you just look at the numbers, it's very confusing. Let's take schema of 0, which gives us the ratio of 2. And the bucket boundary of 1 is where it all starts. So to get the next boundary, you just multiply it with the ratio, which is 2. So you get 2, and then 4, and then 8, and so on. And if you want to lower the resolution, it means you have to make the buckets bigger. So we go to the schema minus 1. And the ratio becomes 2 power of 2, which is 4. If you look at the first number line and the second number line, it is similar to just merging consecutive buckets together, and you get the new bucket boundaries for the new histogram. Similarly, you go on reducing the resolution, you just merge the consecutive buckets together. Let's see in the other direction, where we are increasing the resolution of histogram. We again start with the ratio 2, which is schema 0. So you have the bucket boundary 1 and 2. When you want to increase the resolution, the ratio now becomes 2 power of 1 by 2. So you just add another boundary in between those two buckets, and now you have two buckets between the boundaries 1 and 2. If you want to increase the resolution again, you just add another boundary in between the previous buckets. So that's how it goes on. we'll see why this power of 2 is required later. Like this power of 2 keeps the ratio between each boundaries same. And now because for a schema, the bucket boundaries are predefined, now you can give an index for every bucket. We start with the index 0 for the bucket which has the upper bound of 1. And we just increase the number on the right side, decrease the number on the left side. Are you all with me here right now? Okay. So now that we have built up this knowledge base of how we index the buckets, let's finally take an example of a histogram. This histogram has a schema of 0, which means the bucket boundaries jump with a ratio of 2. Uh, and you see there are 4 buckets that are filled, then there are 2 buckets that are empty, and then there is another bucket that is filled. So we have schema 0, count equals to 11, and sum, which is very trivial. So now let's look at the positive spans. If you look at the slice of positive spans, it has 2 things, 0, 4 and 2, 1. So the 0, 4 tells that the first bucket starts at index 0, and from there are 4 buckets that are filled, so 0, 4. And then 2, 1 tells that after the previous set of buckets, there are 2 empty gaps in between, and there is another bucket filled. So that is how encoding of these buckets work. If there were no gaps, then you just start with the 0 and the 0 or whatever index the first bucket is, and the length of how many buckets you have, and that precisely gives you the layout of bucket, because with the help of these index and the schema, you can tell what are the bucket boundaries. And then we store the actual values itself. We delta encode, which means if you look at 2 and the second bucket is 1, which means the delta is -1. So we store 2, -1, and so on. It's the delta with the previous value. So this is how we encode histograms. And all the time series is now combined into a single time series. All this time, Prometheus just stored a float value with the time series. The timestamp was int, the value was float. Now we are overhauling the entire storage to support this new data structure, where it will be a single time series, and the value stored here will be this complex data structure that we saw right now. And coming to the significance of the powers, the 2 power of minus schema, you can take any histogram and decrease its resolution by combining the buckets. If you look at the first diagram, there are 4 buckets, and which is of schema 0. And if you wanted to reduce the resolution, you would go to schema -1, which will make the ratio as 4. And for that, you just add up the buckets and create a new histogram. So 1 plus 3 got added to 4, 2 plus 4 got added to 6, and now you have the new histogram, which just has a lower resolution, but the same observations. If you want to decrease the resolution further, you do the same thing. Why this is important? So if you have a histogram of one schema, and you want to add or do arithmetic of another histogram which has a different schema, it is similar to currently it's similar to having 2 histograms of different bucket layout. Right now you cannot combine them or do anything between them if the buckets are not compatible. Right now, but with this native histograms, you can lower the resolution of a histogram which has a higher resolution and then combine it. In this example on the top left, it has a higher resolution compared to the histogram on the top right. And I have color coded such that they are all on the same side. Like the blue columns on the left side are both merged together, so 1 plus 3, and that becomes a single bucket in the low resolution. And you add that up with the histogram on the right side, and you get the new histogram. So now you can do mix and match different histograms of different resolutions by converting the high resolution to a low resolution. Okay, now that we know about native histograms, how do we actually instrument this? So from client Golang 1.14 onwards, which is not out yet, but I think it will be out soon, or you can use the main branch of client Golang, you just remove the buckets field in your instrumentation like you don't have to care about defining your buckets anymore. And you add a new field called native histogram bucket factor. Here I have given the number of 1.2. Let's see what this is. It refers to the ratio here. Like you don't have to precisely choose the ratio or the schema. You just have to give a rough estimate of what's the ratio you want between two consecutive buckets. Because we chose 1/2, the closest schema which comes to this is schema number 2, which has the ratio of 1.189. So the client will automatically choose schema 2 for you. And it will build the histograms with the schema 2. But with just this, if the number of buckets can grow indefinitely, and it can just take up a lot of memory. So there is another protection here. You can define what's the maximum number of buckets you want to store. So what happens if it goes beyond 150 buckets? The client will just switch to a low resolution. So let's say you cross 150 buckets with the ratio of 1.2, which shows the schema, which shows the schema 1. It just switches to schema 2, where the ratio is bigger, 1.414, and hence you get a lower resolution, but you don't blow up the memory. It just goes to a lower resolution. There are few other instrumentation options in this, which are also considered before going to a low resolution, but we won't discuss it here. Okay, now that we have instrumented our code, how do we use this in Prometheus? So Prometheus adds a new feature flag called native histograms. So what happens when you enable this is, Prometheus will negotiate protobuf scraping as the primary thing with the target. And these native histograms are only served as protobuf because they are more efficient this way. We are still exploring ways to expose this as a text format. So not only are the native histograms served in the protobuf, all your metrics will now be served as protobuf. Yeah, so this is how you enable it in Prometheus, and it will just automatically start scraping native histograms for you and store them in Prometheus. So how are these native histograms better? It gives you more affordable partitioning. So what is partitioning here? For example, if you had HTTP request seconds, and you wanted to have break down time series into status codes. For example, HTTP request seconds of status 200, then status 500. That's called partitioning. So how is it more affordable right now? So previously, you saw that one time series was created for every bucket. So it creates cardinality problems. It takes a lot of index space. Now the index space is reduced quite dramatically because let's say you had 15 buckets. All of the 15 or 17 time series are now converted into a single time series. And because we can store all the histogram buckets together, it gives you a better compression, so it takes less space, though you have way more buckets than previous. And you saw in the span representation, like how you represent the buckets. It is very concise. It's a sparse histogram. So there are zero cost for unused buckets. For example, previously, if you had defined 15 buckets, whether it be a status code of 200 or 500, it will consume all the 15 buckets. But now, if, for example, you have a histogram for 500 requests, and let's say you are only facing a timeout request, like timeout problem, then only one bucket will be filled for the timeout, and you won't pay for all the other buckets that are not used. And now, because you can control the accuracy between the ratio between the buckets, and that now we don't have the plus infinity bucket, your quantiles will be more accurate than usual most of the time. And because of the power of two example that we saw, like addition of two histograms, now you can aggregate histogram across different label space or across time without worrying about they being incompatible. And the configuration is very easy. I have found myself, like, I don't want to define the buckets because what if I need a different bucket later? So that anxiety always remained in me. So I'm very excited that the configuration for this is very simple. You just define a number and you have all the buckets filled that you want. But there is one con here. There are no predefined buckets. Like we just give the schema and the client will define the buckets for you. So it's possible if previously you defined a bucket exactly for the SLO that you are defining, that will give you 100% accuracy for your quantile estimations. Here, there might be a small error. It's you cannot predefine it, but let's see our goals milestone and what we are planning next. I think I have some time, so I'll go over them in a little bit detail. So phase one, which is done right now, is we can scrape and store the integer histograms. When I say integer histograms, uh, the bucket values are just the count, which are integers. You cannot have float. But when you query, like if you take a rate of histograms, the bucket values can be float. Though we can represent them in the queries, we cannot store them right now. And you have basic PromQL support, which Björn is going to talk more about. And alerting rules will work, but if you are using, if you are templating your alerting like annotations with the value of the query, and if the query produces native histograms, that will have the float value of 0. So you can't template native histograms properly right now. And you can have recording rules right now which produces float. For example, if you take a quantile of histograms, it's going to give you a float value. But if the recording rule produces a native histogram right now, you can't store it because that's a float histogram, which we don't support yet. And remote write is supported for these native histograms, but I think remote storages have to catch up on this development first. Right now, client Golang supports it, and client Java has a separate branch called sparse histogram because supporting this breaks quite a few things. So if you want to try it in Java, you can go to the sparse histogram branch in the client Java repo. So phase two, the thing that we are working on right now. We first want to add support for float and gauge histograms. Gauge histograms is like the bucket values are not a counters. A float in the sense like the bucket values can be float, and with some extended PromQL support. Now, adding support for float histograms will automatically add support for recording rules that produce native histograms. Like recording rules will produce float histograms, and then we can store it. That's the #1 priority that we are working on right now. And there are few features that we left out of the initial iterations, like federation, in-memory snapshot during shutdown, and out-of-order ingestion. Those don't support native histograms right now. There are few extended goals. I won't go into much details. Like, it is possible we can do efficient counter detection because we gave space to save some metadata with native histograms where you can jump a lot of samples and make queries efficient by not checking every sample for counter detection, a counter reset detection. And we will have graph view in Prometheus UI, which is mostly going to be heat maps and some other things, and support in lots of other clients. And we hope to add custom bucket boundaries in these native histograms. Okay, so native histograms will be in version 2.40. But when is it coming out? The answer is now. So I'm actually doing a live publish. Yay. So you can use native histograms right now. The client Golang 1.14 is not out. So until that is released, you have to use the main branch of client Golang, and you can try it out.
It was just released.
Yes. Yeah. Really? Oh, nice. Okay, so client Golang 1.14 is out. Okay. So that is it for my talk. Thank you for attending this. I think we have 2 minutes for questions before Björn can take over. Yes. You can use the mic.
You said that you already have support for PromQL for new histograms, but you didn't show how to use PromQL for new histograms.
Yes, that will be next talk by Björn.
Hi.
Hi.
How does that native histogram would look like in text format, like when we do slash metrics? Like,
So it's not available in text format right now. It is only served via protobuf.
okay.
Okay, so you have to like Prometheus, when you enable it in Prometheus, it will negotiate protobuf to you. It will negotiate protobuf for you, and it will scrape the native histograms via protobuf. Maybe if you can just do a get request for protobuf, you can see protobuf, but I don't think it will be readable.
Okay.
At least for now.
Thanks.
Okay.
Okay.
I wanted to ask, like, about the number of buckets. You said there is, like, you can impose a limit, but will they be reset, like, between scrapes? So when will this be reset?
Reset, yeah, good question. So there were few parameters in the client that I didn't talk about. I think you can set how often do you want it to be reset so that you can make space for new buckets. For example, if your precision got very low because of a lot of buckets, I think you have an option to reset periodically for, let's say, every half an hour or 1 hour. You reset it, so you start the histogram fresh. So it's there in client.
When you switch the resolution automatically, do you have to compact the spans inside the data structure somehow in the background?
Sorry, can you repeat that again?
When you switch the resolution between the span, because the client says you are above the 150 buckets that you said, do you have to compact on the server side the spans?
Okay, so I will go to this one. So when the resolution is, I think your question was in the client, when the number of bucket limit is crossed, how does it change to a lower resolution? Is it?
When you switch it on the client side, you send the new resolution to the server. So on the server side, you have stored the old resolution, right?
Yeah, so the resolution is part of every histogram, like the schema tells you the resolution. So server doesn't need to worry about what the client is doing. If the client sends a particular resolution, it will just store that resolution. If the client decides to change the resolution for the next scrape, the Prometheus server will happily just ingest that resolution. So changing the resolution is decided by the client and not the server.
Did you consider using Prometheus text exposition format for new histograms? Because I think that protobuf format isn't very convenient comparing to text exposition format from user's perspective, and many exporters, Prometheus exporters, don't support protobuf format for exporting. So I think that it would be better to add support for new histograms for Prometheus text exposition format.
Okay, I don't think I understood that question very well. Can you repeat the question?
The question was, did you consider using Prometheus text exposition format for new histograms?
Prometheus exposition, yes. So we have something in progress to add a, you can say, experimental text format in open metrics, which will be a very simple representation of the native histograms. That's the thing that we are looking at next, to add a text format, right? Thank you.